Hey everyone, today we're jumping into one of the big ones, Newton's third law. But forget just memorizing a definition. We're going to use it to crack a classic physics puzzle, one that's probably tripped you up before. Ready? Let's get into it.
So, here it is, the classic horse and cart problem. Think about it for a second. If the horse pulls the cart, and the cart pulls the horse back with the exact same force, how in the world do they go anywhere? I mean, it sounds like they should be stuck in place forever, right? It feels like a total paradox. Well, that's exactly what we're going to solve.
Okay, to get to the bottom of this, we've got to go straight to the source, Sir Isaac Newton. Now, you've heard this 1,000 times, I know. For every action, there is an equal and opposite reaction. But what if the way we usually think about that sentence is actually the problem? Let's dig a little deeper. All right, let's just cut through all the old-timey language. The core idea is actually super simple. Forces are never lonely. They always come in pairs. You can't have a push without a pushback. You can't have a pull without a pullback. It's like a buy one, get one free deal. Every single time. And for all you math folks out there, here's what it looks like in an equation. The force of A on B is equal to the negative force of B on A. Simple, right? The numbers are the same, the strength is the same, but that little minus sign, that's the whole game. It just means they're pointing in opposite directions. That's it. So, let's bring this down to earth, literally. How do you walk? You might think you're pushing yourself forward, but you're not. With every single step, your foot is actually pushing the entire planet Earth backward. That's the action. And the reaction, the Earth pushes back on your foot with the same force, and that's what propels you forward. Wild, right? Okay, now let's scale this up, way up. Think about a rocket launch. What's it pushing against in the vacuum of space? Nothing. It's not pushing off the ground or the air. A rocket works by throwing stuff, hot gas, out its back end at incredible speed. That's the action. The reaction is that cloud of gas pushing the rocket forward. That's it. It's Newton's third law in its most epic form. Okay, get ready, because this right here, this is the secret. This is the key that unlocks the whole horse and cart puzzle. The forces act on two different bodies. That's why they never cancel each other out. Let that sink in. The whole reason the paradox exists is because we've been looking at the problem completely backwards. So let's just lock in the rules for these force pairs. They're always the same kind of force, like gravity on gravity. They happen at the exact same time. And here's the big one, the most important one. They act on different objects. That's why you can't just say plus F minus F equals 0. You can't, because they're not acting on the same thing.
All right. We have the key. We understand the secret. It's time to go back to that poor horse and cart, stuck in our minds. Let's apply this different bodies rule and put this mystery to bed for good.
Okay, let's break it down nice and easy. Step 1, forget the horse. Just look at the cart. What forces are on it? Well, the horse is pulling it forward. That's it. So, the cart has to move forward. It has to accelerate. Simple. Now, step 2, forget the cart. Just look at the horse. It feels the cart pulling it back, sure. But it's also pushing on the ground, and the ground is pushing it forward. And here's the solution in step 3. As long as that forward push from the ground is stronger than the backward pull from the cart, the horse moves forward. The forces don't cancel because they're not on the same object. Boom. Paradox solved. You see, the whole trick is to isolate one object at a time and only look at the forces acting on that object. This isn't just a party trick. It's one of the most important skills in all of physics. So, you think you've got it? Let's put it to the test. We're going to do a quick fire round of exam questions. Don't worry about the math. Just focus on the concept. Ready to play? First one up from a NEET exam, you've got a weight hanging from a string. You pull it sideways with some force F so the string's at an angle. To hold it there perfectly still, what's going on? What are the forces you need to think about? Remember the rule. Focus only on the weight itself. And the answer is all about balance, or equilibrium. The force F you're pulling with has to be perfectly canceled out by the sideways part of the string's tension. And the upward part of the string's tension has to perfectly cancel out the weight pulling down. When all the forces on that single object add up to 0, it stays put. All right, next challenge. A car is zooming around a circular track. You know it wants to fly off in a straight line. That's inertia. So what's the force that's constantly pulling it inward, forcing it to turn? Where does that centripetal force come from? It's friction. And look, it's our old friend, the action-reaction pair. The tires are trying to push the road outwards. The road, in reaction, pushes the tires inwards. That inward push from the road is the centripetal force. And the maximum speed the car can take that corner, it's all about how much grip, how much friction it can get. Okay, last one. This is a bit of a brain teaser. You have a spring. You cut it into a couple of pieces, one short and one long. Now, think about that smaller piece. Is it more or less stiff than the original spring? How does length affect how springy a spring is? Here's the rule of thumb you need to remember. The shorter the spring, the stiffer it is. That's it. The spring constant, K, is inversely proportional to length. So if you cut a piece that's only 1/3 of the original length, its stiffness, its K value, actually triples. It's 3 times harder to stretch. So after all of this, the horse, the rocket, the exam questions, what's the one thing you absolutely have to remember? It's this one simple question. What object is this force acting on? If you burn that question into your brain and ask it every single time, you will never ever get tricked by a problem like the horse-cart paradox again. It's your secret weapon. And I want to leave you with one last thing to think about. Right now, as you're sitting there, your body is pushing down on your chair because of gravity. That's the action. So, what's the equal and opposite reaction? Where is it and what is it acting on? The answer is happening to you this very second. The physics is everywhere. And now, you know how to see it. Thanks for joining me.